This is Chapter 9, Section 9-3, recording number 1. Okie dokie, so we are now talking about the situation when we have dependent samples. Before it was independent samples for both of these. Now we're talking about independent samples. What do we do? Okay, so I just think this is a great author. He always tries to recap, tries to summarize where we are in the very beginning here. So that's what he's doing right here at the beginning of section 9.3. Tries to explain. In 9.1 we use the z-test. 9.2 we use the t-test. But the t-test in 9.2 was assuming that the samples were independent. Now we're going to use the situation when the samples are dependent. And we say they're dependent if they are paired or matched in some way. They're related in some way. So sometimes you'll see in the literature or in software or whatever, they'll talk about matched pair samples. Okay, so let's take an example here. We want to know whether a drug will affect reaction time. So to test this, to decide, does it make a difference or not? It doesn't have to be reaction time. It could be any number of things, right? It could be, does it affect your blood pressure? Does it affect your sense of smell? Whatever it happens to be. So how do you do this? Well, if you're testing a reaction time for the users, okay, the only way you can decide whether it has an effect on a particular user is to test the reaction time first. In other words, before the drug is taken, and then you test the reaction time afterwards, right? So those are matched pairs. You're testing John Doe before, you're testing John Doe afterwards. So they are dependent, okay? So that's what he's talking about here, okay? I'll let you read that on your own. In some way, the samples are related. And he gives different examples throughout the book here. Here's some other examples talking about a SAT preparation course. You take the test, the sample SAT test beforehand, you take the sample SAT afterwards. Is there a difference after you take the review course? Okay, here's some other examples about where they're not considered to be independent. I'm going to go ahead and let you read that for yourself, okay? Now, this is an important point right here. And I just did the exam. The publisher has software that generates the exams. And I just did one today. And if I'm not mistaken, this question is right there. So the exams are always fair, right? I mean, they're from the publisher. It's not weird stuff that I make up. So unless the publisher makes a mistake, the material will be taken right out of the text. The test will be taken right out of the text. And as I recall, here's something that he talked about in one of the tests. When subjects are matched according to one variable, the matching process does not eliminate the influence of other variables, right? Okay? So you can't control everything. So just matching for one thing doesn't mean that it matches for everything. This is something that's very important here, talking about what's called the Hawthorne Effect. I think he mentions that name somewhere in the book. If people know they're being tested, it can influence the results. There's always a possibility of what's called lurking variables, L-U-R-K-I-N-G, lurking variables, or things that are lurking around, kind of hiding around, and you just don't have any way of knowing what they are. You can't control for them, okay? All right, so here we go. Here's the t-test we're going to use. This author's a great author, but I certainly don't recommend trying to memorize these tables. Okay, but we got to come up with this. What the heck are we even talking about? What are the random variables that we're going to be getting so that we can do this test? So that's a little bit complicated here. Let's see if we can figure this out. Okay, so based on my experience, this little section here, this little subsection here, is kind of hard for students to get their arms around. Let me try to help you. What gets in your way is the notation, the actual notation itself, okay? All right. Keep in mind that this is a study of matched pairs. John Doe is matched with Susie Smith. And using this example up here, students are matched or paired according to some variable that is pertinent, is relevant to the study. Okay, and then one other student is assigned to one group and the other student is assigned to a second group. Okay, so John Doe is matched with Susie Smith, and they're paired according to their IQs, or maybe their class standing. Like you don't want to have students that are dissimilar that are matched. Okay, you want it to have a grade point average are basically the same. Maybe their background is basically the same, whatever. They're going to be matched in some way, okay? And as the author says, just because you control for educational background doesn't mean you control for everything. Maybe John Doe, let's say John and Susie. John and Susie may have went to the same high school, have identical grade point average. But on the other hand, you don't know this, but John is working 40 hours a week, and Susie, her mom and dad are paying for her education, so she doesn't have to work. So you can match on certain things, but you can't match for everything. Everybody's unique, right? So you have to be aware of that. But the key here is that you are looking at not what John gets, not the score that John gets, not the score that Susie gets. You're looking at the delta of the scores. So in a situation where he talks about right here, let's say John's in the group that gets instruction by computers. So maybe John is learning by way of Canvas, and Susie is in a different group. She is going to the traditional classes. She's going to the traditional lecture and discussion method. Okay? So these are the two groups, the Canvas group and the traditional group. Okay, so you're sick of hearing me say this, but now here's an example of why I stress this so much. Tell me, what is the random variable? What's the random variable that we're talking about? It's not so clear, is it? It's not so clear. Okay, so pause the video and think about it. What's the random variable? Pause the video and think about it. Okay, I'm going to trust that you did that. The random variable is not what score did John get. It's not what score did Susie get after the instructions, okay? In this experiment here, we're talking about some sort of the two different methods, and you're going to do something. You're going to test their learning at the end to see what their final exam score is. So it's not the final exam score for John. It's not the final exam score for Susie. Okay? So what is it? It's the delta. It's the difference between the two kids. Okay? That's what the random variable is. So where does he say that exactly? Right here. The difference of the values of the pairs of data. So you take the two kids, John and Susie, and John's score take away Susie's score gives you a data point. So x sub 1 take away x sub 2 gives you a data point. Okay? So the notation makes you crazy. I mean, it's very, very difficult to understand what he's saying here because of this. So that's why I introduced this term delta. Delta means difference in math, okay? So let's say you had 30 kids that you were doing this test on, or 30 pairs of kids, 30 pairs of kids. 30 pairs of kids, that's 60 kids altogether, but you only have 30 pairs because you have John and Susie, you have Billy and Tommy, you have, Mark and Mike, you have Frick and Frack, whatever. Those are the pairs of data that you have. So each one of them, at the end of this experiment, you test their test scores. One of them goes to Canvas, one of them goes to a normal lecture, and you determine, or you calculate it, you have them take the test and you figure it out. So you have 30 data points, all of these little D's. So what does this x sub 1 and x sub 2 refer to? I don't like that notation, but I'm very sympathetic to the author. It's hard to come up with good notation in this situation. What he's saying is that you have group 1 and group 2. This isn't the first data point and the second data point. The data point is the D. So this is what he, if he had the room to write it, what he would really like to be able to do is he'd like to say something like X is the final exam for, Susie and John. And then the next one is Frick and Frack. The next one is Tom and Steve, whatever the names happen to be. So the notation really gets in the way here, in my opinion. So what the author chose to do, and it's very difficult to come up with a better solution, this little subscript of 1, this little subscript of 2 refers to group 1 and group 2, and X and X are the matched pair. So it's the matched pair from group, and the first, you got somebody from 1, you got somebody from 2. So you have the first guy. So to really make sense of this, what they really need, but it's just again, the subscripts and the notation gets in the way. You need another little indicator here, another index, like like over here on the left-hand side, pair number 1, pair number 1. Pair number 2, pair number 2, pair number 3, pair number 4. And then it's the first person and the second person out of each of these pairs, okay? So the notation kind of gets in your way. So just kind of ignore the notation on this one example here, or this one case, because it just gets in your way. Just keep in mind that what we're looking at are data points. The data points are the differences, the deltas. The random variable is the difference between each of the pairs of data. Each of the matched pairs give you a data point, and that's a random variable. Okay, so if the deltas are to be considered as a random variable, well then, great, as we used to say when I was a kid, groovy. It has its own the data point, or these data points, the deltas, they have their own distribution. Therefore, you can find the mean of the deltas, okay? He's calling them D's. So you can find the mean of the D's, that's the D bar. You just add them all up, divide by n. That n is the number of data points. You can come up with a standard deviation for the D's, for the deltas, okay? You can find the so-called standard error of the D's. Boom, there it is, okay? And finally, here is the test value. What's on top? The observed value. Boom, there it is. Take away the expected value. Boom, there it is. That's the mu sub D, which is in this case probably going. Okay, so let me distinguish those. Remember that the expected value, that's the mu sub D. That's the mu, that's the population. Okay, so the population delta, and by the null hypothesis is always going to be that there is no difference. So the mu sub D is typically going to be 0. Okay, so we're saying that this expected difference is going to be 0. And then on the bottom, you have the standard error. So it's always the same as before. It's the how surprised are you? And then on the bottom is the yardstick. Okay. So he explains all that. I hope I helped you understand this. The notation makes you crazy. Absolutely. Okay. And this, being the standard error is the standard deviation divided by the square root of n. That comes from the central limit theorem, because everything is more or less normally distributed. So we're kind of treating everything as having a normal distribution. And if you look back on the central limit theorem, what we always did was we divided by the square root of n to kind of make the numbers come out better. Okay, so these are the assumptions that we're going to make. I'll let you read that for yourself. It has to be random. Sample data is dependent. Again, has to be normally distributed. Okay, and here's the formula. There's the formula. What a mess, huh? What a mess. But you don't have to memorize it. That's the good news, okay? So let's end the tape now, and on the next one, we're going to go through and we're going to do an example.